Whitfield. Our next speaker is James Whitfield, who will talk about chemical group theory for quantum simulation.
So, hello everyone, I'm James Whitfield. I'm at UGent now, recently moved from University of Vienna. I started out my academic career studying math and chemistry. And for me, I didn't really understand how these two things fit together. They were just actually an accident that I was studying chemistry. And what it turned out was that by the time I reached my senior year and started learning about group theory, it was quite amazing to see everything come full circle. So for me, group theory is one of the first places where I understood how chemistry and mathematics come together. And hopefully I can give you some ideas of what we're trying to do here. I really want this talk to be very much grounded, so it's going to be a bit different than some of the other talks in the sense that it's not going to be so theoretical. It will be theoretical, of course, but it will be feet on the ground theoretical. So we want to think about how to actually solve instances. So I will talk about computational chemistry first. Then we'll talk about how to actually implement some symmetry considerations using different formulations of quantum simulations. I assume most people are fairly familiar with quantum simulation, so I won't go into too much basic detail about quantum simulation. And then I want to take some time out to discuss industrial grade quantum computing. So really, how do we actually make these things practical and realizable and something that a company wants to invest in or that a company wants to put time into? Or how do we actually build quantum computers in a roadmap sort of situation? So first, computational chemistry. So I like to think of computational chemistry as kind of two parts. First part is just that you want to understand molecules. So John Popel won the Nobel Prize in the 90s, and he gave during his Nobel Prize lecture this idea of a model chemistry. Model chemistry is this idea that you can take an algorithm and apply it to any molecule. So here we have molecular instances on the left, and then on the right we have different model chemistries. So by model chemistry, I mean you pick out some descriptive resolution, saying I'm going to include so many points per atom, or I'm going to include so many basis functions, and then I'm going to pick out an approximation. So here's some sort of density functional theory with some functional and some basis on the right-hand side here. Here. And then on the other side, you have some molecule from some set of instances. So this large space, and you might want to simulate any molecule. And I'll give some examples of how this actually comes into play from the sense of what you're actually going to want to compute. So often we hear the question, when will quantum computers beat classical computers? But I think that's not a realistic question. And I'll explain how to actually answer this. Because what we really want to solve is the Schrodinger equation. This is the time-dependent Schrodinger equation. But we don't just want to solve it accurately, we also want to solve it quickly. We don't want to just solve it quickly, we also want to solve it accurately. And you kind of have a trade-off between these two. And so how do we actually reach to some point where we can actually be competitive with density functional theory or couple cluster or different approximations that you can make is going to be a major theme of the talk. In using group theory, if someone were to write a new quantum chemistry algorithm today, the first thing they would implement is group theory. You wouldn't even consider your code finished until you've implemented group theory, because almost every single molecule has these ideas from group theory. And we'll come back to this in a second. But first, let me give some examples of molecular instances that one might encounter in practice. So this is, takes me back to undergrad. So we have different molecules, so some radical, and we want to know what the different energies for each one of these species are, and then get the difference between the energies. And once we have these energies, we can say something about how quickly the reaction will occur at different temperatures. We can understand the internal energy. We can compute rotational spectra and things like this. We can talk about barrier heights. So as I rotate this double bond. So for those of you who didn't take chemistry back in the day, this is the dark wedge means that it's coming out of the plane. And the dash wedge is going into the plane. So it's kind of a 3D representation of things. So here, the barrier height, you're rotating this planar molecule, and you want to rotate it this way, and then see what the energy is as you rotate. So this is kind of the idea. So we want to know what the difference between these two different configurations are. You might want to know how likely is it that an atom or a molecule will absorb a proton. And then for a real concrete example, in the 1980s, I suppose someone older than me would know much better, but the ozone problem, the hole in the ozone was discovered. And this is the reactions that you find in the ozone layer. And these reactions were discovered as a result of an actual problem. So someone is studying the ozone, notices there's a large hole, and they want to know what the reaction mechanisms are, what are the likely pathways, what are the energetics of this. And this would be an actual problem that you would give to a computational chemist who's working alongside an atmospheric chemist, and they want to know about the properties of this reaction. And they would want to know using computational chemistry. So it's not that computational chemistry says, okay, here's a problem we can't solve any other way, but really we just want the solution anyway. We want the solution to be good, and we want it to be quick. So this brings us to quantum computer simulations. So quantum computer simulations goes back to the 1980s with Richard Feynman suggesting that simulating quantum systems is perhaps hard because we're using classical hardware. So if we use quantum hardware, then perhaps it would be much easier. We can do the simulation in one-to-one time correspondence. But then this leads to a bunch of questions about how to actually encode this into quantum hardware. There's many different ideas about this. And the basic structure of all the algorithms is to first pick an encoding. So we say we have some particular way of encoding the state. First quantization, second quantization, sparse matrix decomposition. We can talk about variational state parameterizations and different ways of encoding it. And you see there's different ideas from the literature about encoding it. And then once we encode the system, you have to initialize the initial, you have to create the initial state. So as we heard this morning, creating the initial state needs to be somehow efficient. So creating initial states can be as hard as you wish. And this is QMA, the essence of QMA theory, is the idea of preparing initial states. And so you have to prepare some sort of initial state. Then you want to do propagation to extract the information. There's much more I could say about the propagation to extract information, but essentially this is phase estimation. There's other techniques that you can use that we heard about this morning in our first talk. But the main idea, again, is that you want to do some sort of quantum simulation, some sort of time evolution to extract information. So at some level, you can think of quantum simulation as utilizing the fact that as quantum systems evolve, the entanglement grows in time. So low entanglement wave functions can be captured with matrix product states. And because we're doing time evolution to understand the system, the entanglement's growing in time, meaning that the approximation from matrix product states is getting worse in time. So we're really looking at systems that become entangled in time. We want to understand their dynamics, properties of it, barrier heights, rotational conformations, things like this, stability. And we want to extract this information. We do so by propagating. So the whole point of a quantum computer, you can think of it as just a quantum time evolver. So if you can do quantum time evolution classically, then you can do quantum computation. So to me, quantum computation is just, the BQP would be the class of quantum simulations that you can do efficiently. Okay, so in this talk, I'm going to talk about group theory and its applications to the first three of these applications. So first, quantization. We can drop qubits. So essentially by dropping the spin degrees of freedom, we'll gain quite a bit. Second, quantization, we won't be able to lose any qubits, but what we will be able to do is do projections into spin eigenstates, and I'll talk about why that's important. Black box simulation is some ongoing work, and I'll talk about how this relates to Lie algebras. So first, the set of symmetries. The symmetry group of the Hamiltonian is a set of all operators A that commute with the Hamiltonian. You can show this as a group. It has closure, identity, associativity, and inverses. So this is a group. And then it simplifies the numerical simulation because it allows you to block diagonalize your Hamiltonian according to your group structure. And these are your irreducible representations. And one example is the number operator. So these could label how many particles you have. So the one particle sector, the two particle sector, the three particle sector, so on and so forth. It could be point groups. So when I talk about a planar molecule, then you have a plane of symmetry. And then the point group then gets broken up into how it transforms under these different operations. And you can do many different things that symmetry comes into play. But in all molecules, so as you go to larger and larger instances, the point group will play less and less of a role because your molecules just naturally become less symmetrical because it only takes adding in one substituent to make it no longer symmetrical. But what you always have is certain symmetries that are always present. So you have, in fermionic wave functions, you always have this anti-symmetry property. So anti-symmetry essentially, well, I assume everyone knows, when I swap the ith coordinate with the jth coordinate, then I pick up a minus sign. This is fairly simple, but when you do a Schmidt decomposition, it's not as clear what happens when I swap these things. And this is where group theory starts to come into play. And we'll see the symmetric group show up and many other nice things appear when you start looking at, instead of the full wave function, this x being combined coordinates of both space and spin, and then you do a Schmidt decomposition to some function of just space and some function of just spin. These spin eigenfunctions, you want them to be also have good quantum numbers in terms of s squared and sz. We can do this using different techniques, and I'll discuss in a very high level some of them. But essentially, the energy of the Hamiltonian only depends on the spatial part. So you can think that if I'm carrying around the spin coordinates, it's too much information. So I can just throw away the spin coordinates. As long as I pick out the spatial coordinates appropriately, then I don't need spin at all. This is the main idea of the problem. OK, so that's the wave function. The wave function needs to be antisymmetric, but your Hamiltonian is a many-particle, is a many-body Hamiltonian. And if we talk about the kinetic energy, the potential energy, and the electron-electron interaction is T, V, and W, then what you have is just some set of coordinates, and these Hamiltonians are invariant under relabeling of these coordinates. So the Hamiltonian itself, because it's identical particles, won't know the difference between swapping all of them. So in many senses, a lot of the quantum algorithms, a lot of the effort that goes into a quantum algorithm is losing distinguishability. So when you talk about the Jordan-Wigner transform or the Bravais-Keteb transform, all these things are to make qubits, which are distinguishable objects, become indistinguishable fermions. So fermions and bosons would both have this property that they're invariant under this permutation. But this permutation group Sn has a lot of properties going back to the 1900s with Young tableaus, and throughout the entire 1900s, people thought about these things. And the preacher Young, Abram Young, or I forget his first name. So Young came up with these tableaus. This is actually a Young frame. But this Young frame corresponds to some decomposition of the permutation group. So this is a permutation that's cycle structures. So you can think of it as cycle structures if you know these things. If you don't, just think of it as a frame that's labeling your spin coordinates. So what spin you have. So the total spin and the projection with the z coordinate, you would get from just looking at just the frame. And you put things into the frame, and you get out either wild tableaus or young tableaus. But all these things come about because you have the symmetric group acting on the Hamiltonian. The unitary group shows up as a result of the fact that unitary group, where you act one unitary acting on every single coordinate separately, this also is invariant under permutations. So then you have these maximally commuting groups. So then when you pick out labels for the permutation group and labels for the unitary group, then you can label all the eigenstates that have the same energy. So any questions about the very, very sketchiest outlines of Young tableaus? Okay. So first, I'll go through first quantization. This is first. So in first quantization, we can actually apply Young's projection operators. So going back to Abrams and Lloyd's algorithm back in the 90s, which Seth Lloyd could also tell us about. It's quite a nice algorithm where you are able to do anti-symmetry or symmetrization of the wave function by doing permutations. So in first quantization, each electron has its own grid. So you have some grid where coordinate R1 could be the x coordinate, the y coordinate, and the z coordinate, and then either spin up or spin down. And this would encode just the coordinates of the first one on its own grid. Then you have the second set of qubits, which also encodes the next electron, and then you have the same number of registers as you do particles. So then, as I said a few minutes ago, these Young tableaus will label the spin will coordinate with the spin function that you're going to drop. And then when you drop the spin functions, you just have to keep track of what permutation you're in. And you can do this by applying partial symmetrization, partial anti-symmetrization based on these Young tableaus. And what that'll give you is in a spatial wave function that has the correct symmetries. This allows us to lose in qubits, which is great. So if I'm doing a simulation that required 100 qubits and I had 30 fermions, then now I have 270, which is really what we're looking for. So here, this talk is about constant speedups. So constant factors. So we want to actually improve the algorithm overall. So we heard about exponential improvement, but this is really when you start scaling up problems. When you start thinking about how problems scale, then you're going to get different considerations. But if you just want your algorithm to run on existing hardware and run quickly, then you want to do as many constant speedups as you can. So here we're losing in qubits, which makes the simulation simpler. You can also do projections into point groups by taking into account this Wigner projection operators, which I won't describe in too much detail. This is a rather short talk. Okay? Actually, I will talk about the Wigner projection operators, excuse me. So the second quantization. In second quantization, what we actually do implement is Wigner projection operators. And these are essentially to project into irreducible representations. This would be, so there's different approaches to constructing symmetry adapted or spin adapted wave functions. You can either do it constructively. So there's work by Kenji Sujisaki in Japan, where they're building deterministic constructions by actually building up using these branching diagrams, where you use some branching diagram to raise and lower the spin state in order to construct proper spin eigenfunctions. And the approach that I chose was more of an analytic approach where you want to project into a particular irreducible representation. So you can project into a particular spin state or project into a particular irreducible representation. So if you're interested in something like a buckyball, you can really solve the buckyball in practice. Not big, there's a huge number of electrons, but there's a huge amount of symmetry, which means that your system, the Hamiltonian breaks up into very small blocks, and you can handle each one individually, which is essentially what we want to do here. So in quantum simulation, as I pointed out, the main hard part of it is preparing the initial state. So by projecting into a subspace, you're going to get a better overlap with the state you're interested in. So when you talk about spin eigenfunctions, you talk about a determinantal basis where you just have some state that's not necessarily spin adapted or not necessarily a spin eigenfunction, then there can be many, many states that also have the same spatial components, and then you'll have a tough time actually picking out a particular state that has large overlap with a particular spin sector. So it allows for better initial states, but you don't get any qubit savings. And for those of you who don't know second quantization is where you have one qubit per one basis function, so per site. So if you have 15 sites, you need 15 qubits. And we're going to assume that each qubit is symmetry adapted to begin with. And if it's symmetry adapted, then we already know how the representation of the group will act on this symmetry adapted basis function. So if something, by knowing the characters of the group, we can implement this actual irreducible representation, where you take these irreducible representations and you do a Fourier transform over the group. And then inside the group algebra, you apply the representation of the group action onto the wave function, which you can do because you assume that the orbitals are symmetry adapted. And then you do the Fourier transform back, and this essentially has the same exact structure as phase estimation. So phase estimation, you do the Fourier transform over the control register. You apply some gates based on what the control register says. You undo the Fourier transform, and you measure. And this is essentially what we're doing here. And this is based on work from 2004, where someone else is looking at Clebsch-Gordon coefficients and other things of a similar nature. Okay? So we can go further and think about other things we can do also inside of second quantization. So between first and second quantization, there was always a huge gap in terms of number of operations. So when we talk about, in the literature, you'll see that in first quantization, normally the cost of the algorithm scales with the number of particles. So you have something like n squared interactions, so you have n squared interactions, so you have n squared scaling. But in second quantization, quite often what you see is that you have a scaling with the number of basis functions. And you can understand this because you're simulating in all symmetry sectors. So if you simulate in all symmetry sectors, then you're going to scale with the size of the full Hamiltonian, which is dependent on the number of basis functions. But in reality, you shouldn't scale with the number of basis functions. You should really scale with the number of interactions when you have fixed particle number. So if we think about the continuum limit of the interaction terms, you have W, which is your electron-electron interaction, and V, which is your electron-nuclear interaction. These two things should commute in the continuum limit. So if we have a interaction that's, so the Coulomb operator between the electrons and the Coulomb operator between the electron and nuclear terms should commute. But quite often when we project into a basis of Gaussians or whatever, quite often we don't have this exactly satisfied. But you can enforce this, and if you enforce this, then what you get is that this interaction term, instead of having 4 indices, now only has 2. And because it has 2 indices, moreover, we can actually just think about computing distances between occupied orbitals. So we say, is this orbital occupied? Is this orbital occupied? And you compute the distance between them, and that allows you to do it in a way that scales with the number of particles rather than the number of basis functions. So in the previous second quantized simulations, you're simulating the interaction inside of all Fock sectors, which means that you're getting something that's scaling with the basis set size rather than something scaling with the particle number. So then you compute both the electron-nuclear interaction and the electron-electron interaction based on occupancies, which means that now instead of scaling with the number of basis functions, they scale with the number of electrons. So the cost for implementing the electron-electron interaction now scales quadratically with the number of electrons that you have. And implementing the electron-nuclear term scales linearly with the number of electrons. But because doing local basis transforms inside of second quantization is quite difficult, the best thing you can do for the kinetic energy is just to implement it in the old fashion, where you implement inside of all Fock sectors. So then it scales as m squared. So this is somehow an improvement in the sense that we want to get to a simulation that's in one single Fock sector, which will allow us to improve the entire cost of second quantization. This is as good as it gets, as far as I know. I mean, if anyone has ideas about how to implement the unitary group within second quantization, then let's talk more. Okay. So we heard this morning about exponential improvements in quantum simulations for black box algorithms. So for the black box simulation algorithms, essentially what you need is a way to compute matrix elements of a sparse matrix. So going back to 3 papers by Peter Love and co-authors, he looks at how to do oracular simulation based on determinant of the wave function. This is using the Slater-Codon rules, where you take a determinant, another determinant, and you compute the matrix element. And this is efficient and simple to compute, but the determinant of the wave functions are not eigenfunctions of S squared and SZ. So as I pointed out in the beginning of the talk, we can use symmetry adaptation and these ideas of group theory to actually make symmetry-adapted wave functions. Symmetry-adapted wave functions that are eigenfunctions of both S squared and SZ. And if we do this, then we have a basis that will carry the irreducible representations. And in that way, we can actually write down the Hamiltonian in a spin-free form, where each one of these terms is just your excitation operator summed over both the alpha and beta states. So and there's simple rules for generating the matrix elements of these generators. And once you have the generators for the Lie algebra, you can just apply these commutation relations to get all the other terms. In this way, you get a sparse representation for a subsector of the matrix. So rather than simulating all m choose n different determinants, you now are simulating inside of a smaller fraction of this subspace. This is kind of the idea. So then this still needs to be sketched out a bit more and to work out the exact ways of computing the oracle. But essentially, this is the idea. Okay. So the results for the first and second quantization showed up inside of a paper from 2013. So In this talk, I didn't go into too much detail about the unitary group and the symmetric group because there's a huge literature. So in chemistry, it goes back to the 1960s, where Matsons wrote spin-free quantum chemistry 1. And then he wrote spin-free quantum chemistry 2, spin-free quantum chemistry 3, spin-free quantum chemistry 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then it's somewhere around the 20s, all with the same title, spin-free quantum chemistry. Along with other authors, so Paulus and many other people worked on this. But this has all essentially been worked out throughout the 60s, 70s, 80s, to the point where the entire theory is just waiting for you to pick up a book and learn it. One of the things I did find very interesting about learning chemical group theory is that when you look at a lot of the group theory textbooks in physics, you often get things about solid-state physics, high-energy physics, and many other topics where group theory shows up, but it's a bit tougher to find things about chemistry. So, I mean, you can find books about chemistry, but it's usually at a very low level, but to really find something that handles it at the level of Young tableaus and unitary group, you have to look a bit harder. And there's a lot of work worked out, entire books dedicated to the idea of building spin eigenfunctions. So a lot of the work is just importing these ideas from the classical literature and updating it for the quantum setting. So I wasn't really sure how much detail to go into about the unitary group and the symmetric group because it's either interesting to you and you know it already, or it's not interesting to you and you don't want to know it. But of course, there are these papers. You can look at them, and they will have more details. And there's many references to books and papers that are good. But essentially, molecular problems have symmetries, and you want to exploit the symmetries to make some constant improvements. Instead of getting polynomial speedups or quadratic speedups, we just want to get the whatever quantum speedup you're going to get, fine, and then get some improvement on that algorithm. And there's waiting to be had is application of solid-state simulations. So in solid-state physics, they also use group theory as much as possible. But a very different flavor of it, but essentially in the same vein. Crystallographic groups instead of point groups. And these Oracular methods is still in progress, and it's not published yet. Also, the paper by Kenji should be coming out sometime in the near future. But I'm also waiting for this to show up. Okay, so with the remainder of my time, I'm not sure how much time I had, but how much time do I have left? It's going to be short. Okay, so for industrial grade quantum computing, so one of the important things that I wanted to really illustrate and emphasize during this talk was that in terms of chemistry, in terms of actual chemists, they are interested in solving actual problems. And it's not necessarily a question of how you solve it, but rather that you did solve it, and that you solved it in a way that's useful for me as an experimentalist, or useful for me as a pharmacist, or useful for me as someone else, right? So then you can start asking questions about industrial grade quantum computing. So when will it be good enough to tell someone in industry something that they couldn't have gotten another way? Or at least give them some information they didn't have before. Maybe you can come up with the information and someone else can validate it with another method, or someone develops a method just to deal with this type of molecule. But you can take your method and apply it to things. And this is the idea, again, of Popel's model chemistry. So I got to thinking about these ideas about industrial chemistry because there's a lot of investment going on in quantum computing. So you had D-Wave come out with their magic box. Microsoft has quite an active group working on many different aspects of quantum computing. IBM is both doing experiments as well as theory, as we just heard. Google has many representatives that are now also trying to build adiabatic quantum simulators. Intel just made an investment with Delft to try and boost their capacity to quantum computing. And I imagine there will be more companies that are pushing into quantum computing as these things become more and more relevant. So then the question you have to ask yourself is, okay, as a company, what are they interested in? The same way I ask myself, as a chemist, what are my fellow chemists interested in? So how do I actually get something that's interesting to chemists or to companies or to someone in a way that's not just epsilons and deltas and scaling within and you know, when we have 1,000 qubits, what are we going to do then? I think we really need to think about the roadmap to getting to 1,000 qubits. So no one's going to give you enough money to build 1,000 qubits in the next 2 months or the next 3 years or the next 10 years, maybe 10 years. I don't know. Depends on how good our experimentalists are. But I think one way of really checking how good our experimentalists are, and one way of keeping track of how good we're doing as a community and as a field, is by looking at validation. So in classical chemistry, the original algorithms for doing quantum chemistry were done by hand. So when they say computers, it's really a person who sits in a room with a pencil and paper and does all the integrals for Hartree-Fock, and he tells them what the integrals are, and you give them the algorithm, and they follow the whole algorithm through, and they say, here's the answer to your Hartree-Fock calculation, by hand. But when you do something by hand, that means you really have to take small instances. You can't scale up. You can't say, I'm going to do bigger algorithms. I'm not going to do this, that, and the third. And we have to think about quantum computers the same exact way. Quantum computers right now don't go that fast. They're not that big. They're not, there's nowhere near 1,000, nowhere near 300 qubits. But if we think about something that we have now, so we've done a few small experiments looking at hydrogen, helium hydride. There was the reaction dynamics algorithm by a group out of China, Yefeng Du's group. But there's a few small experiments. But what I'd really like to see out of experimentalists, I don't think there's an experimentalist here, but if there are, let's talk about what you should do. What you should do is really take a test set of molecules. So this test set of molecules is actually really funny, because I got this slide from this DFT poll. So they do a poll every year of DFT functionals, and they just take whatever results from the poll, make a new functional, and then test out how good it does on the test set. So you can just take a random molecular, a random algorithm and apply it to everything, and then you just see what answers you get out. So it doesn't really matter what technique you use, so it's kind of approach agnostic, but there's experimental values for what it should be. So these are just some small atomization problems, and you actually compute what these are, take whatever approximation you need, just brutalize the system until you can actually compute it. If you have 10 qubits, then you fit in 10 qubits all in. You have 12 qubits, and you fit them all into 12 qubits. And the point is in that way you can say, all right, well, I got very bad root mean square error this year, but next year when I have 20 qubits, my root mean square error went down. And you can plot over time how well you're doing. And you can really think about how you're actually going to scale up to 1,000 qubits, to where you really can start doing biomolecules, or you can start doing large molecules faster than density functional theory. But I think this is what's really needed, to really see some actual work done. So classical computers are very, very good at what they do. So starting with Intel in 1971, they built the first commercial chip. It was put inside of a calculator. And now we have dedicated hardware for doing molecular dynamics. So Anton was built by D.E. Shaw just to do molecular dynamics. And they can do huge molecular dynamics for long amounts of time. The hardware is set up only to evaluate a certain type of potential and evaluate it quickly, go through everything and do all of that things. You have cloud computing. Now everything's on the cloud. You have Amazon and different companies that offer cloud computing. Supercomputers all over the world, competing to see who's running the fastest supercomputer. And of course, GPUs. So GPUs, I think, is the most interesting from the standpoint of quantum computing. So GPUs take a lot of small processors, put them all on a chip, and there's a certain way that they all have to do the same exact thing, and you set up programming such that it's almost like parallelization within one chip. So it's a bunch of cheap chips on one single processor, and then it does many different things at the same time, almost like almost like a sweatshop, where you have the shoes coming in, the materials, and people tie them together, and then the next person puts in the laces, the next person puts in the rubber sole, and then it comes out, and you can do many, many shoes at one time. Okay, you're not going to make highest quality, but you make many shoes. And so for quantum computing, I think in the short term, what we might think about is the same way GPUs don't try and beat the CPU. They don't try and do things faster than the CPU. They try to do different things than the CPU. They try and make things that you can actually get done to help out the CPU. And I think quantum computers, for the short term, if you can't beat them, join them. I think as quantum simulation progresses, I think rather than thinking about scaling up in terms of size, we think about scaling up in terms of speed. So if we have short algorithms that we can run, short simulations, short processes, short algorithms that we can run, but we can run them fast enough that we can compete with classical algorithms, then I think that's where we really want to be. You need to construct better quantum to classical interfaces. So how do you actually input and output information to your quantum hardware from the CPU and get it back from the CPU? And some examples for this might be interesting is doing some sort of quantum region within a molecular dynamics simulation, where you're really interested in some, I don't know, metal complex, and you just treat the metal complex with high quality quantum simulation or some sort of high accuracy simulation within a DFT embedding. So DFT here is density functional theory, not discrete Fourier transforms. So again, just to drive in the point a bit more, I think that if you think about algorithms in terms of simulation algorithms, you can think about it as what you really want is fast algorithms with high accuracy. This is idealized. So in many ways, complexity theory tells us that you can't get there. That you can push towards that boundary, but there's going to be a limit. And this is what complexity theory says. Yeah? So it's some hard limit. Building a slow and low accuracy algorithm, there's really no point in doing that, other than maybe theory or something like this. But there's no practical point. But building a slow algorithm with high accuracy or a fast algorithm with low accuracy, both of these things are useful. So density functional theory is probably more inside this area. And what we've been shooting for inside of quantum computing is to replace algorithms inside this area. So when you have full configuration interaction, some sort of exact diagonalization, and that would be a slow algorithm with high accuracy. Density functional theory, there's no systematic way to improve it, but it's quick. And you can run millions of molecules, millions. And you can actually make a database of the data, and you can say which one's closest to what I'm looking for. And you can just run it over an entire set of things, not the highest accuracy, but you can really get things done. And if we think about quantum technology the same exact way, we have fast enough quantum technology, then we can do short algorithms that will allow us to do something that will be interesting. And it doesn't need to be that it's faster than a classical computer. So a classical computer with 40 gigabytes of RAM can simulate quite a large quantum system. But if you can build a quantum system, even though it can be simulated classically, if you can do the simulation fast enough that it makes sense to offload that computation to the quantum processor so the CPU can handle whatever else it's doing and then come back, then that's a better idea. So if you're talking about something like Grover search, rather than searching through an entire database, you search through some small subsection, break the problem up into small pieces, and you send it off to 15 different quantum coprocessors, each one without error correction. So when you talk about error correction, your codes are normally going to be, some multiplicative factor times whatever number of qubits you actually need logical. So if you can do quantum simulations where you don't need error correction and you don't need long coherence times, but you can still get out something interesting, then I think that's what we really need to aim for as algorithm designers. So I think looking at asymptotic scaling is interesting, but I think looking at low-cost simulations that can happen today, tomorrow, next year, 3 or 4 years in the future, to approach these things is really what we want to do as a community. Okay. So that's about all I wanted to say. So I want to first thank my PhD supervisor, Alon Spuraguzik, Frank Strate. So I moved from Vienna to Ghent, but I'm still in Frank's group, because Frank is in 2 groups, for whatever reason. I guess if they don't force you to choose, then you don't have to decide. I had many collaborators and colleagues over the years, many of them in the room. And I also want to thank the organizers for inviting me to come. There's many people who paid me money, and here's my email address if you want to ask more, or if you have some ideas about group theory or about short quantum simulations.
Any questions?
So for the unerror-corrected steps, how many, what would be sort of a lower bound on the number of gate operations you'd have to be able to do successfully in order for this to be actually worthwhile?
Okay, so I don't know a number, but I can tell you just based on ideas about quantum simulation. So if you think about quantum simulation, the point is you need to be able to do quantum simulations you can't do classically. So in time-dependent density matrix renormalization group methods, there's a runaway time. So if you can do a simulation longer than the runaway time, then you can say you can do something that's at least hard classically. Maybe there's a technique that can do it classically, but you want to do something that's difficult for the quantum computer, for a classical computer. Not necessarily to beat it, but difficult. So I don't have a lower bound yet, but I'm thinking about it.
Which DFT code has millions and millions of molecules?
All of them, actually. So it turns out that if you take a DFT code, it runs quick enough that you just put it on a supercomputer and you run on each node a different density functional theory. So there's screensavers that just do density functional theory all day. So you leave your screensaver on and it runs calculations on your computer, and they have millions of molecules. There was a paper last year by, I don't remember the name, but one of these group machine learning groups that's interested in quantum chemistry. They just did 1 million molecules just because, I mean, you have computational power. I mean, the molecules aren't huge, but you can do them. I mean, you're not talking about biomolecules. You're talking about small molecules in all different shapes and sizes. You know, just put in carbons here. Instead of carbon, you replace it with silicon. And then, okay, you put in fluorine. Okay, you put in bromine. You put in, and you just make different combinations.
Do they use any force field?
No. Density functional theory is ab initio. I mean, it's semi-ab initio because you have to make some uncontrolled approximations, and you don't necessarily, there's no systematic way to improve it. But like I said, it's low accuracy, but it's fast. And if you can do 1 million molecules, then I can screen through things. And screening is really one of the major applications of electronic structure. So you want to screen through molecules to look for something that has the best gap.
A single point energy or any properties of the chemical system?
They're computing properties, as well as single point energies. I mean, single point energies give you a lot about the properties, right? You compute it at different geometries, and you can tell a lot about the system anyways. Also, if you compute a single point energy, you usually get out a wave function. You can use a wave function to compute whatever property you want. Well, not whatever property, but.
Are there more questions?
So this kind of goes back to some of the technical pieces where you talk about sort of removing spins from the fermionic wave functions.
Yes.
And I'm just wondering, there are some complexes in which you want to keep the spins. Is that right, or are you saying that for the most interesting problems for a computational chemist, you do in fact want to get rid of that piece?
Let me say it the following way. So the spin can be interesting. So quite often when people are doing chemistry, the question is a lot of times which spin state is lower. So you want to know, is the triplet lower than the singlet, or so on and so forth. So, but still what you would compute is the singlet energy, and then you would compute the triplet energy. So the only time you'd really want to keep spin around is if spin is not a good quantum number. So I mean, in some instances, spin is not a good quantum number. So when you start talking about heavy atoms, then you have to do different couplings. So nuclear spin starts to couple with the electronic spin and spin orbital coupling, blah, blah, blah. But these are corrections that you make. And then you'd have the different good quantum number, and you'd make everything symmetry adapted to that quantum number instead. So spin is always a good quantum number. And there's different things that you would call spin. So whether it's electron spin or whether it's some sort of coupled spin, then it's always going to be a good quantum number. And you're never going to want to keep it around, unless maybe you have some sort of spin flipping going on. But
More questions? Actually, maybe I can ask you one more question. So people often say that the hardness of a quantum simulation depends on how entangled the state is. Is there sort of a nice way of saying what that means precisely for these states where there's symmetry, where you have fermions and these other kinds of structural constraints?
So entanglement in fermions is a bit complicated, but I mean, not that complicated, but normally you have to talk about so fermions are automatically correlated because they're antisymmetric, right, at some level, but then you can talk about entanglement that's actually entanglement between the orbital modes. And then if you start talking about entanglement between the orbital modes, then you can actually look at how much entanglement you have by doing bipartition cuts and just computing relative entropies and things like that. But I don't have a more concrete answer than that. I would say that it has to be enough entanglement that it's difficult to simulate classically.
Thanks. Any more questions? If not, let's thank James again, and after this we have a break.